All right, in this video, we're going to talk about mass percent and empirical and molecular formula. So let's go ahead and get started. All right, so the first thing is mass percent or percent composition. Those two terms can be used interchangeably. It depends on who's writing the question for your AP, free response or whatnot, according to which version you'll get. But they're the same thing. Now, when we take any percentage, it's part over whole times 100, and that's equal to our percentage. Say, for instance, we want to figure out how many girls were in our classroom. So we would take the number of girls, that would be our part, divided by the total number of people in our classroom, that would be our whole. When we divided those and multiplied by 100, we would get percentage of girls. Now, the same thing can be applied to your compounds, to chemistry. So if I want to figure out the mass percent or the percent composition of every single element that I have in this compound, I would do part over whole. So if I want to figure out the mass percent of carbon, I would do the mass of carbon divided by the total mass. The mass of hydrogen would be the mass of hydrogen divided by the total mass, and you guys get the idea. So what I did is I worked through this example problem here with ethanol. All right, the first thing we have to be able to figure out is the molar mass of ethanol put together. So it's C2H5OH. And so when I add this molar mass up on the periodic table, I got something around 46 grams. Now, to figure out the percent of carbon in that sample, I take the mass of the carbon. Since there's 2 there, then I have to make sure that I add 2 carbons, which will be 24, divided by 46, which is my molar mass. And when I multiply by that by 100, I get something around 52%. When I did hydrogen, you have 6 hydrogen there. So 1 hydrogen is 1 gram. So 6 hydrogens would be around 6 grams. So 6 divided by the total mass times 100 would equal to 13%. And then if you look at this last one, oxygen, there's 1 oxygen here, so it has a mass of 16 divided by the total mass times 100 gives you something around 35%. Now, make sure when you do these percentages, they can vary from these numbers a little bit, but the main thing is that these should all add up to equal 100%. Now we're moving along to empirical formula. Now, what an empirical formula is a simplified mole-to-mole relationship between the elements in a compound. So let's say that we get this compound, we have no clue what it is. Well, we have to do some sort of analysis to be able to determine what the chemical makeup is. So we'll take that sample and we'll burn it. And when we burn it, we get lots of different products that we know should happen. For instance, if I take something that's carbon-based and I burn it, then I should be able to get carbon dioxide out of it. If I take something that's hydrogen-based and I burn it, then I should get water out of that compound. And this is stuff that you might remember from your combustion formulas. Whenever I burn something that's combustion, that means it's reacting with O2. That's something you might remember from pre-AP. So when I take all of that information, I then can find mass percents. So once I have the mass percent, I then can figure out my empirical formula. What is the simplified version of the chemical makeup? And our whole goal here is to figure out these mole-to-mole relationships. That's what we're trying to do. So I put together kind of a step-by-step process of what you can do to be able to figure out an empirical formula. The very first thing you need to do is change your mass percent to grams. What we can do here is assume that we have a 100-gram sample. So if any percentage is out of 100, right? So if I have a 59 mass percent, then how many grams of that will be out of 100? That will be 59 grams. So whatever the mass percent is, I just directly convert to grams. If I have a 6% for the mass percent, it will be 6 grams. Then I use dimensional analysis to convert those grams to moles of each element. What we're looking for is a mole-to-mole relationship between each element. So I need to know moles of each element that I have there. Then, once I have moles of each element, I divide each of them by the smallest number of moles. This is going to give me the whole number mole-to-mole relationships that I can write in my empirical formula. Step 4, you only do if you don't get whole numbers from step 3. If you don't have whole numbers, let's say you get like 2.5 or something like that, then you want to multiply everything by some multiple in order to get a whole number. And you'll see that in one of the examples we're working with. Now, once you figure out an empirical formula, you then can figure out the molecular formula. Now, here's the difference between the two. Molecular formula is the actual mole-to-mole relationships. Empirical formula is just a simplified version. So say, for instance, I have 3/6 as a fraction. 3/6 would be my quote-unquote molecular formula. But I know that I can simplify 3/6. I can simplify 3/6 to 1/2. 1/2 would be my simplified version, and that is what an empirical formula is kind of like. So, in order to figure out a molecular formula, I first have to find an empirical formula. After that, I calculate the molar mass of the empirical formula. And the way that I do this is just by looking at the periodic table. Then step 3, I have to figure out the whole number multiple. So how I do this is I take a molar mass that's given. Now, sometimes this molar mass isn't given, so I like to call it actual molar mass. So the actual molar mass. If that molar mass is not given, then you will have to find it somewhere previously in the problem. This goes back to when we were talking about how to find a molar mass of something, whether you take the grams divided by the moles, or you use that molar mass equals dRT over P, the molar mass kitty cat equation. So that's how, if you aren't given to this, you can find that value. Once you find this value, you then take the molar mass of the empirical formula, and that's what you found in step 2 here, and you divide molar mass of actual divided by molar mass of the empirical formula. And this should give you a whole number here, whether it be 2, 3, or even 1. Once you have this whole number, you're going to distribute it through your empirical formula. We're going to go through some examples, and this will make more sense to you. Okay, so now let's go through an example. So what we want to do here is find the empirical and molecular formula for the compound that contains Cl, C, and H. We also are given a molar mass that's 98.96. So this is the actual molar mass that's given to us. We don't have to find it some way. And this is going to help us for the molecular formula. So I have it written over here on the board of how we're going to work that out. We're going to go through step by step. So step 1 is we're going to change all of these percentages that we have here, the 24.27, the 71.65, and the 4.07. We're changing those percentages to grams because we're assuming there's 100 grams. So if there's 4.07%, then we can assume that's 4.07 grams. So we have the grams of each listed here. Our next thing is we want to get into moles of each of those compounds. So that's why we have the molar masses. Chlorine's molar mass is 35, carbon's is 12, and hydrogen's is 1. We do our dimensional analysis here, and we get 2.02 moles, 2.02 moles, and 4.07 moles. Now, once we have moles of each, we then have to figure out which is the smallest number out of all of these. The smallest number is 2.02. So to get whole number relationships between these, we're going to divide every single one of these by that smallest number. And you see how we're getting whole numbers out of that. We have Cl, which is a 1, to C, 1 to H2. So that's telling us we have a 1 to 1 to 2 relationship as far as Cl, C, and H goes. From there, we can determine our empirical formula. So we have CH2Cl2 as my empirical formula. Now to get ready for the molecular formula, I then am going to figure out my molar mass. Once I find my molar mass, I then take the actual molar mass divided by the molar mass of the empirical formula, and I get the number 2.